In 1865, James Clerk Maxwell, possessing formal training in mathematics and physics, recognized the problems and theories of electromagnetism and tried to re-express them in a mathematical language. This gave rise to a concise set of equations that describe all electromagnetic fields, from the electronics that dominate our modern lives to our base physical interactions. Maxwell's initial inspiration was from Michael Faraday's work on electromagnetic induction. Born in South London in 1791, Michael Faraday was a man with no inherited wealth or contacts. At a young age, he taught himself science and entertained his inquiring mind by reading books and attending lectures. In 1813, Faraday began working for Humphrey Davy, president of the Royal Institution, who would go on to help Faraday become a respected chemist. Faraday would then go on to aid in the identification of benzene and iodine. This translated well into experimental physics, where he went on to discover electromagnetic induction in 1831. His work would have a massive ripple effect within the scientific community, influencing the work of both Maxwell and Einstein, and many more.
What is Faraday's law? Here we have a magnet and a coil connected to an ammeter. While the magnet is stationary in the coil, the ammeter reads 0. However, as soon as the magnet is moved through the loop, there is a current produced. The direction of this current is dependent on the direction of the magnet's motion, and also which way round the magnet is. This is because the magnetic flux is now changing instead of being constant, and that is essentially Faraday's law. A changing magnetic flux produces an electromotive force. Faraday managed to express the relationship between magnetic flux and induced EMF mathematically. This became known as Faraday's law of magnetic induction.
This law shows that if you move a magnet near a conducting loop, it will drive a current around the loop. The Greek symbol phi is the external magnetic flux. N is the number of coils in the loop. Doing the derivative of phi represents what we saw earlier. A stationary magnetic field has no effect, only one that changes over time does. The negative sign represents Lenz's law. Here we have a regular metal tube and a magnet. If you drop something down the tube, it just falls. But if we drop a magnet down, you can see that it falls much slower. This is because the current induced in the tube has its own magnetic field, which is in an opposite direction to the moving magnet. It will always be the case that the EMF will create a magnetic field, opposing the magnet that induced it. Maxwell took this further by showing that an electric field that varies over space is paired with a magnetic field that varies over time. This now applies to all electromagnetic phenomena. So here on the left-hand side, we have the curl of the electric field. The right-hand side represents the magnetic field changing over time. We still have this negative sign as Lenz's law still holds. This equation shows that the electric field and the magnetic field are intrinsically linked.
Through understanding Faraday's law, along with Lenz's and Maxwell's adaptations, we can now fully appreciate the true magnitude of his discovery. Faraday combined theoretical and experimental physics beautifully. The relationship between electric and magnetic fields has been a key factor in pushing both our understanding and technological developments forward.